Welcome back to part 2 of the AP ECE Chemistry Chapter 7 Covalent Bonding Problem Set 2012. It's Mr. Wilkosz. We're looking at the last two parts of problem 19. So we have CO plus. Again, we're drawing lots of Lewis structures. This is an accepted structure for this positively charged ion. And then also ClO3 is an accepted structure for this. You will encounter ones once in a while where you are obliged to put a single electron on an atom, less frequently than more stable ones, but this is a possibility. Let's take a look at problem 23. For problem 23, you're asked to consider hydrozoic acid, and they give you a structure for it, and you are asked to come up with two forms. And so here are our two forms. These are actually the two resonance structures. This could be a triple bond between these two nitrogens, or flip it through here and be a triple bond between these two nitrogens right here. And those are resonance forms because the basic structure of the molecule is not changing. Hydrogen is connected to a nitrogen that's connected to another nitrogen, and that nitrogen is connected to another nitrogen. Same deal here. Hydrogen to nitrogen, nitrogen to nitrogen, and then nitrogen to nitrogen once more. So these are your two possible resonance forms for this. You're actually shifting around a triple bond. Is this considered, part B, a resonance form? And the answer is no. You're not following the general format. You're actually starting to make a ring within this, and by making a ring within this, you're not using all of your electrons. You're changing the arrangement of the atoms, so this is not a resonance form. Let's take a look at problem 29. In problem 29, you're asked to compare two Lewis structures in terms of their formal charge. So you're given structure 1 and structure 2. Structure 1 and structure 2. What I've done underneath is compare and calculate out the formal charge. So this first column right here, the 1, 6, 5, and 6 are sort of the number of electrons that these atoms initially brought to the bonding situation. Then we minus from that the number of bonds connected to it, the number of lines connected to each individual atom, and underneath that, that final row is for the number of dots, the number of unshared electrons that the atom has. And structure 1 comes out with all zeros. That's good, maybe not if you want to win Powerball, but it is good if you want to be a stable Lewis structure. For this other possible arrangement, we get two zeros, but then a -1 and a +1. So here's your calculation format for formal charge over here for a given atom, and structure 1 is superior in terms of stability. And I've been saying that it's, happier or whatever, but the truth is that it's just more reasonable. It's more likely to occur. Happier is sort of an oversimplification, but formal charges that are nearer to 0 will be more likely. Let's take a look at 31. For problem 31, you are asked to predict the geometry of parts A, B, C, and D. So you really have to draw the Lewis structures to get an idea of what they should be and try to consider formal charges. So I've drawn out Lewis structures for each of these things, and it looks like I got a little lazy on this one because there should be 3 versions of this to represent the resonance. Still, you can kind of figure out what the structures for each of these should be. It's pretty clear that A is linear, straight line across here, no unshared pairs of electrons to displace these two atoms around the central carbon, the oxygen and the sulfur, so they're going to go straight across to be as far apart as possible according to Vesper theory. For the second one, it might be a little obscured that the fact this should really be linear. So this has got a basic structure of trigonal bipyramidal, because there's 5 items surrounding, quote, items surrounding the central iodine. The 5 items are 2 bromines and then 3 unshared pairs of electrons. They're going to try to separate as far apart as possible, so B should be linear as well. This only one resonance form that I drew for nitrate is trigonal planar. When you draw your Lewis structures, it's totally okay to go in your cardinal directions up, down, left, and right. But you got to realize that this oxygen here is really kind of swung downward to accommodate Vesper theory, valence shell electron pair repulsion. And this should be trigonal planar to separate the 3 things as far apart as possible. I tried to give you another diagram here to help represent what's really going on with radon tetrafluoride. We've got 6 total things surrounding the central atom, so 4 of them are along the equator, these fluorines, 2 going back into the screen, 2 coming out at you, and then the electron pairs are going up and down. So this should be square planar.